I would like to make a brief announcement. So one of our speakers, Professor Jiangping Hu from the Institute for Physics, Chinese Academy of Science, brought us some journals. The journal is called Physics, and the journal has three different articles in them. One by Barbara about Shoucheng, one by Jiangping, and the third one is an interview of Shoucheng. So there's three very special articles, and so feel free to take them. They are in the registration desk, but unfortunately they only have the Chinese version. So for those, you can try to learn Chinese, or you. But the English version of Barbara's article is on the memorial website.
Good. It's on already. Yeah. All right, are we ready to start?
Okay, welcome everybody back to our intense session. When I first met Shoucheng, I wanted to get him interested in what I'm interested in because I was interviewing for postdoc. And I got some hint from other people that if you mention spin, he'll be happy. So this session is on spintronics, and our first speaker is Dan Arovas.
Thanks. All right, so this was just, I guess, to focus, but there's this hidden message here, thanks to the organizers. And so really just a great job, Xiaoliang and Steve, and also I want to thank Noel. They've just done a magnificent job here putting on a workshop that I think would have made Shoucheng extremely happy. So, great job to all of you. So here's a photo I have of Shoucheng. Shoucheng was a collaborator and a friend, and I think this is from a conference in Israel maybe about 10 years ago. I know that Eugene was there because I have some other photos I might show later or tonight that include that. And I like this picture of Shoucheng very much. He's sort of arms on his hips, confident, seeing all this old disorganized stuff around him and thinking, let's clean this shit up, And, and so that, all right, so rather than try to compress a 60-minute talk into 30 minutes or 35 minutes as the case may be, I'm going to try to expand a 15-minute talk into 25 minutes. And to start that, I want to tell a little bit of a funny story about Shoucheng. It starts with this first paper that we collaborated on. I checked the citation count last night, as Joe said. Okay, so it's not much, but I really think this gave him the idea about the 4D quantum Hall effect. Yeah. So Shoucheng, no end of the superlatives one can say about him, but he wasn't really a jokester. But he did really like he appreciated a good sense of humor, as we heard from Andrei Bernavig this morning. He really enjoyed his 50th birthday roast, and we had lots of good times together. Incidentally, I didn't check the paper that Andrei referred to in his talk of mine, which if it had epsilon citations, at least it has epsilon plus 1 now. But I'm reminded, after hearing Andrei speak about it, of a brilliant self-effacing inversion of Newton due to my friend Andy Cohen, which is, if I have not seen far, it is because giants are standing on my shoulders. Anyway, so as part of this project, some simple model. Actually, it did involve some AKLT stuff in here, but we needed at one point we needed to know something about some beta ansatz stuff, which I don't think entered into the paper, but we needed this book. And let me just say a bit, for the younger people, the millennials here especially, I admire all you greatly. You're incredibly brilliant and accomplished. But if you'll just stop thinking about avocado toast for a moment, I just want to tell you a little bit of history. So it was back in the day, and this was in the late 80s, when you needed the book, you would go to a building called a library. And the library was a place where you had books and journals. Now, you didn't just get them on your cell phone, okay? But to find them, you'd have to go look them up in a catalog. And there's a catalog filled with cards called a card catalog. And in the library at UC Santa Barbara, Shoucheng and I went over there, and because we were looking for this particular book. I don't know how we had heard about it, but there was a little scraps of paper and a pencil that you could write down here. Again, Shoucheng, actually, this is more a story about me, but Shoucheng plays the essential role of the straight man in this story. And the straight man is a very important part of humor. So well, they didn't have any pencils, so we needed to look up the catalog index, which I remember to this day, QC 174 C65, QC 173.4 C65 W56. Indeed, I looked it up last night, and it's still QC 173.4 C65 W56. Well, we went over to this place in the stacks, and the book was not there. So we went to the librarian. That's a person that sits at a desk, and we explained our problem, and the librarian said, "Oh, we'll put out a call for it. Check back in a week." Well, so a week later, I'm at this KITP workshop. Shoucheng and I were still talking, and we weren't worried about being scooped on this paper, and and so he said, "Oh, Dan, let's go over and see if we can find that book." And I said, "Yeah, QC 173.4 C65 W56." And Shoucheng just sort of stood there and looked at me and said, "Have you ever seen Rain Man?" which is, for those of you who don't know, it's a movie about an autistic savant. So one of my earliest memories of Shoucheng is thinking that I was an idiot. All right. Well, anyway, that's my Shoucheng story. So this is a very brief story. It's a project that a student of mine worked on and then left before we revised the paper to resubmit it. But I remember I actually talked with Shoucheng a bit about this over the phone, because every once in a while we would chat about things, and that he liked the idea, so maybe it's somehow appropriate. So the idea is to understand something about quantum nucleation of skyrmions and chiral magnets. Okay, skyrmions, we heard, is Stuart here? Okay, that's good, because I don't think I referred to any of his papers in this talk. Skyrmions are these topological defects in this case, an O3 model. There's this integer Pontragin index, which describes the winding of the n hat vector around the sphere. And so here's an example of a skyrmion configuration, real space down there. That's a what Stewart was calling a Nail skyrmion. And so, there are emergent, many particle, particle-like objects comprised of lots of individual spins, and they might have some progress for applications in spintronics and logic and quantum information. So that's all left to people like Stewart. They're finite energy configurations of the O3 ferromagnet. There's a very nice identity due to Bolomoni, or inequality, that says that if you integrate the exchange energy, the integral of the gradient of n squared, that it's always larger than or equal to 4 pi times this integer Pontragin index in units of the spin stiffness. And so at low temperatures, one expects that Q not equal to 0 excitations, that they should be suppressed by Boltzmann factors. But skyrmions and skyrmion crystals can be energetically favored in the presence of additional competing interactions. For example, we heard about Zhang-Maria, which has sort of two incarnations, Dresselhaus and Rashba, which will correspond to broken inversion, symmetry, and bulk, or at a surface. These will prefer respectively block and nail type skyrmion configurations. There's anisotropy. There's Zeeman energy. And so these have actually been observed in various chiral magnets, manganese silicon, iron cobalt silicon, iron germanium, 3D crystals in thin films. They can compete with other phases. Here is is this a, okay, yeah. So here's I think actually Stewart showed some of these data from this paper by you and company. So here's temperature, and here's magnetic field, and there's some state H, which is the helical state. Then there's the skyrmion crystal phase. Then there is this is like a paramagnetic phase up here, where the field is really high. You align all the spins, and here there's some incomplete list of highlights. I'm not going to get to mentioning. This is where I would have mentioned Stewart, but he told me yesterday he wasn't going to be here. And so here's helical skyrmion crystal, so this is a comparison of actual experiment with some theoretical prediction, so our project is to think about skyrmion nucleation. So remember all that experimental stuff, because I'm not going to explain any of it. So for example, micromagnetic simulations of current-induced motion in the presence of geometrical boundaries showed the nucleation of skyrmions. This is all classical physics. There was some nice work using spin-polarized current injection to write and delete skyrmions in these palladium iron surface bilayers. There's some generation of skyrmion crystals and skyrmion trains in ultra-thin cobalt films using some short current pulses, and blowing skyrmion bubbles. This was sort of cute through a geometrical constriction, and then various micromagnetic simulations of skyrmion creation via local heating. These are actual real things. Our project is actually to take a step back from all that reality and just think, at least in principle, of the idea of quantum nucleation of skyrmions. So the scenario that we sort of imagine is, so you remember that phase diagram. So you've got your Zhang-Maria interaction is already present, and now let's imagine you start to crank up the magnetic field. At very, very high fields, of course, you align all the spins, but when you dip below a critical field, you create this skyrmion crystal. So we were thinking, well, suppose you could just take a magnetized tip or something and bring it close to your sample and put the field in the opposite direction, coming from the tip a bit, so you reduce the field in some local region. Then if the field is lower than the critical value for the skyrmion crystal, then it should be at some point it would prefer to make a single skyrmion in that region. And so you would nucleate a skyrmion, and this, in what we're looking at, we're thinking of 0 temperature, and so this is some sort of instanton problem. You want quantum nucleation of this topological defect, and then of course what's sort of a bit unusual about this is that you have topological charge, and so there's no way to see this sort of nucleation if you had a purely continuum model. Somehow you have to deal with the discreteness. So here's the idea again. You bring down some tip, and then you create some sort of spots where you have some reduced magnetic field, and in that spot we want to see a skyrmion nucleate. And here's a nice paper from Mohit Randaria's group where they look here as a function of so the A is anisotropy, and J is exchange, D is Jalshinsky-Maria, which can come in either this D perp, I think, is the Rashba. So this is the pure Dresselhaus. This is the pure Rashba. For the Rashba, this skyrmion crystal phase is more expanded. So these are some theoretical calculations, and then again, this is this data I showed previously by you, showing where the skyrmion crystal appears here. So again, we're just thinking of doing some sort of local quench in this case, and then seeing what happens. So people did work on this issue of thermal nucleation of skyrmions. This is some Monte Carlo calculation, and over here, if you could see in the inset, here's some sort of cartoon of a configurational coordinate in one direction and some energy. And so if there's if the ferromagnetic and the skyrmion configurations are local minima, then you can imagine that at finite temperature you could go over the barrier, and because the distance from the bottom of the well to the barrier is different size, then there will be different inverse mean lifetimes depending on where you start out. And so there's work like this, even some attempt to calibrate these data, which are not given in any physical units, but in terms of like Monte Carlo time steps, some attempt to calibrate these two experiments in actual systems where these things are observed. But again, this is like a Kramers type thing, not the quantum nucleation that we're talking about. Okay, so quantum tunneling. So again, skyrmion nucleation is going to involve a change in topology with delta Q is, we'll assume, plus or minus 1. This was emphasized in Haldane's beautiful 1988 paper on the O3 nonlinear sigma model and the Heisenberg antiferromagnet in 2 dimensions. He understood the importance of these topology changing hedgehog defects in the action, and it can't be understood in terms of a continuum model. Can't do it. It's like the Keystone pipeline without eminent domain or something like that. And so in dimensionless units we have some Hamiltonian, which has exchange. There's anisotropy. There's magnetic field, and then there's DM. For us, Rashba, and so there's some overall energy scale, and there are some dimensionless parameters. So we're not really going to be so serious about trying to model real systems that we have to pay attention to the actual detailed values here. This is sort of more an exercise, a proof of principle. So the first order of business then is to explore the classical phase diagram, compare the energies of the ferromagnetic and single skyrmion states in the presence of this local spot where the magnetic field is lowered. So you could solve the for the skyrmion configuration, and then we could sort of tweak it to the lattice. It's nice to just solve this quickly and then fit it to the lattice and to get the lattice solution. Not essential, but and then here's this change in the local reduction of the magnetic field, and this is the spot, this diameter of this circular spot in units of the underlying lattice spacing. And if you make some one-parameter interpolation, between the Q equals 0, no skyrmion, and Q equals -1 skyrmion configuration. So this is some particular interpolation. I won't go into what it is. But you can see that as a function of the value of the field at the center, that's when the field is very low in the center here, out at infinity it's 2 in these dimensionless units, then the skyrmion configuration is lower energy than the no skyrmion configuration, and then eventually they will cross. So basically we'd like to know how to get quantum mechanically from here over to there. Okay, well, this is an old story. So now we promote these variables to some time-dependent variables and endow them with Euclidean time dynamics of quantum spins. So we'll assume that this is a model where there's some local spin S on each site. This is the Berry phase term that gives you the rate at which the solid angle subtended by the spin at lattice site R changes with time. And this is that Hamiltonian that I flashed a few slides ago. And then following Callan and Coleman, we want to compute the matrix, a Euclidean matrix element of e to the minus beta h between, let's say, the two states in the ferromagnetic configuration. And to compute this by the spin coherent state path integral. We evaluate this by a simple and probably simplistic collective coordinate approach. And this entails basically expressing the dynamics of this whole set of these spin fields in terms of just two functions, some complex function and its complex conjugate. This sort of collective coordinate approach has been used elsewhere in modeling the decay of metastable Bose-Einstein condensates, and in fact you could even compare it with a more proper calculation where you include all these, find the many spin instanton, and it gives you qualitatively similar results, at least in that case. So all right, so interlude, spin tunneling, and the tool is spin coherent states. Chris Henley, another outstanding condensed matter theorist who left us too soon. So learned a lot from his papers on this. Also Anupam Garg, and a lot of this goes back to early work on tunneling in a magnetic field in a beautiful paper by Jinendra Jain and Steve Kivelson from the late 80s. I remember because some of that technology I had learned from Steve and used in my PhD thesis a couple of years before. And so, well, here's the idea, for a single spin, we have the Euclidean Lagrangian, which is, I times S times the solid angle, time derivative plus the Hamiltonian, which is a function of, we could express it in terms of, let's say, the cosine of the polar angle, and then the azimuthal angle phi. And then, of course, you get these equations of motion by extremizing your action. And so you'll notice I figures in here. And during the instanton, this quantity u, which is cosine theta, becomes imaginary. And if you plot the energy contours for some sort of tunneling problem, like Chris had looked at, you may find that you want to tunnel from, let's say, this state over here, up to, let's say, down, and there's a saddle point between you. What are we to do? Well, when you do this analytic continuation, what happens is this saddle point turns into a center, and vice versa. So if you go off into imaginary space or imaginary cosine polar angle, then you do have these equipotentials connecting the beginning and the end of your instanton event, and you just have to integrate the Berry phase along here, because we know that the Hamiltonian itself will be preserved, energy will be preserved along this by the equations of motion, and so again, in this very nice paper by Steve and Jinendra, they apply a version of this to tunneling problems in in a magnetic field of electrons, let's say, in the lowest Landau level. This idea has applications also here in spin tunneling. And again, there's some very nice work by Anupam Garg on small magnetic clusters where this approach is used and compared with experiment, and very, very well. So that's the basic idea. So we say, well, they're smart people. Let's try to do what they did, and so it's convenient for us to express the spin field in terms of these stereographic coordinates u and v, and then you could define this ratio w, which is v over u, and now there's some sort of interpolation. Again, we want to interpolate between the non. Okay, yes, I will proceed apace. Between the non-topological case and the topological one, where there's a skyrmion present, and so when lambda bar is actually equal to the complex conjugate lambda star, then as lambda goes to 0, we recover the ferromagnetic configuration, and we could write the effective action as some function of those collective coordinates. And then basically what we want to do is we want to tunnel through this barrier. And the idea is you follow this imaginary time, imaginary space dynamics going under the barrier. And then when you get over here at this position, then you could just roll down classically this hill. So you go from between those. So again, the instanton is some solution to the saddle point equations. And okay, so there's some. It's a lot easier using the collective coordinates. We don't have to solve as many equations as we did if we had every spin. And during this instanton event, this lambda bar is not equal to lambda star. So that's like saying that the coordinates are not real functions. And the coherent state path integral basically says that you integrate one of these forward from initial data and the other backward from final data. The symmetry of the saddle point equations guarantees that when you emerge from under the barrier, that it's real again and can be interpreted as a classical or semi-classical spin configuration. So all right, so this is basically just standard instanton stuff here. This is again the integrating forward from initial data and backward from final data. To the Conoscenti, there are some details about boundary discontinuities, but it turns out that won't matter here for regions I don't have time to explain. At any rate, if we have some discrete definition of what we mean by the Pontragin index by summing over little plaquettes, then at some point it's going to switch from 0 to 1, and this is like in Duncan's hedgehog. And so basically, this is the instanton event. Okay, we have to go from here, this configuration, to this one. And well, since I'm running out of time and spent too much time on my joke, which I hope was worth it, I'll just show you some pictures. Since I'm not purporting to explain anything anyway, but we can compute this instanton again. Here you see that lambda and lambda bar, the real parts thereof are not equal, and so we can actually in this collective coordinate description get a rather vivid picture of what's happening during this instanton event. In principle, there's a fluctuation determinant to compute, and there is an issue about whether, when you emerge from the barrier, whether you're actually in the skyrmion state or not, or whether you in the process of rolling down here in a discrete lattice, you would actually go through that topology changing transition, and it depends on parameters. Well, that's about it. This is my last physics slide. So so basically what we've done is obtain this instanton action as a function of this local magnetic field shift and the size of this spot. This is some sort of contour plot of the action, and dividing two regions, whether or not when you emerge from the barrier you're in the topological state or not. We have some expression for a tunneling rate. due to the small spot size within it, you don't want to develop a helix. That's pushed up to higher energy. And then again, the system can emerge from the barrier in either of these configurations. And then there are various missing pieces of this, which I'm not sure are going to get done because the student is gone, but maybe another student will be interested in picking up on this, numerically solving for the many body configuration and maybe trying to make some contact with actual materials. Probably need to talk to Stuart to see whether that's anything is even hopeful there, what you might want to try to measure. But that's basically all I'd say. This little project. I want to just share a couple more photos of Shoucheng. And do I have a minute? 30 seconds? No time? Okay.
30 seconds.
Okay, 30 seconds. That's with Jan Meerheim. That's lecturing in Haifa. There's some friends in Akko. More friends in Akko. Here's with our organizer, and this dumpling is Brian. Okay, so.
Sorry, maybe it was clear from what you said, but what did you mean by classical tunneling? Like thermodynamic rather than?
Yeah, just like thermally assisted tunneling, right? Yeah.
So I had a quick suggestion and then a question.
Yeah.
Making a quench by changing the magnetic field might be hard.
Yeah.
But you might want to think about quantum hole ferromagnets, where you could change the density of the gate and suddenly need a skyrmion in the ground state.
Yeah.
And so that might be a more practical, it may have some differences here, but it may be more practical as an experimental platform.
Yeah, I agree. Yeah.
The question is, thinking about that at least, presumably you can't have a conserved SZ.
Right,
So you have to have something that breaks that symmetry, is that right?
Well,
in your case, it's the
yeah,
Shoucheng
right, yeah. Well, the net Berry phase in the tunneling event actually is the action. But it's real because you're. There's no imaginary part. We've checked that. Yeah, in this particular case. Yeah.
So then, can your calculation be generalized to the following problem? So imagine that you prepare the spin spiral configuration. So it's just Heisenberg model. You prepared it in a way that winds, and then you just let it go, and you ask how does it get rid of this winding?
Yeah, right. I mean, years ago, there's work on this in superconductors, right? How phase,
right,
slips nucleate in superconductors, right? So
yeah, but in this case, it's real Heisenberg.
Yeah, no, it's a different. It's not the the Ginsburg-Landau or whatever action, but it's a different action, but it's a similar sort of case of winding, right? So
so there is winding in the plane because you prepared your spin in the plane, but naively to escape this winding in the plane, you have to go to the third direction. So somehow physics appears to be similar.
Yeah.
Just because experiments like this have been done.
All right. Well, maybe I could grab you and. All right.
Due to limited time, let's
Yeah.
move on to the next.